fortunate to have another luminary of the AI field here giving our second keynote speech, Richard Granger from Dartmouth, who has produced a very interesting body of work over quite a period of time, which spans computer science and neuroscience in a very, very interesting way, giving really deep insights into both sides there, as well as touching on mathematics, linguistics, and a host of other areas. And he's written more papers and books on more topics, and I'm going to try to summarize here. He's really been a pioneering cross-disciplinary thinker, which is very much in the cross-disciplinary spirit of these AGI conferences. So he's promised to have a wild mix of different topics related to general intelligence and the brain for us today. So take it away, Richard.
Okay. Can you hear me? Yeah. Let's see what I got here. Right. We were just talking about how, oh wait, sorry. Okay, I got this. That's right. Okay. Oops. All right. Let's start at the beginning. Oh dear. Okay, there we go. Right. Right, I'm going to call it brain engineering, if you will, and the argument's going to be that if we want general intelligence, I don't know if anyone here wants that, that we have to look at things in a way that's extensible. We have to look at things that can talk about perception, low-level perceptual levels, and talk about high-level cognition, and not just try to cobble them together or bridge them, but try to integrate them. Our work began on pure modeling of brain circuitry, and it ended up, it started deducing algorithms that seemed to be in our hands what particular brain circuits were doing, and those started, of course, those different brain areas talk to each other, and as we started to compose these things, we started to find families of algorithms that looked like they were doing something coherent, and I'm going to make a pitch for this. Oh, first of all, it says me, but who actually did the work, a bunch of people who are doing computational work, especially Tony Rodriguez and Eli Bowen, Brent Toffel, Ashok Chandrasekhar, and a bunch of people who are doing biology, especially UNIA, and it was paid for. Right, done my duty. All right, so the basic hypotheses are widely agreed upon in this room, so I'll just breeze through them. In fact, it's an awful lot here that I'm going to breeze through, but I hope it'll be coherent. There's a long-standing gap in AI. The things that AI does well, like Jeopardy, are things that are notoriously hard for people. If things are hard for people, it's easy for AI. Things like vision, long-term memory, language are things that are easy for us and hard for AI. In other words, these things have terrible trouble extending. We're making wonderful strides. In fact, the previous talk was a great jumping off point for this, because the truly inspiring work of people like Joshua, a number of people, is showing us what we can do with these new kinds of so-called deep learning systems. I'll suggest that there are a large family of deep learning systems. We'll introduce one. And the question is how they extend from low level to high level. What biology has to tell us is a useful story from a point of view largely of constraints. That is, what can't possibly be. And the brain is telling us, it's very hard for the brain yet. We can't do the experiments we want to do. It's very hard for it to tell us exactly how it's working. But it's really good. Neuroscience is really good so far at telling us things that are extraordinarily unlikely for brains to be doing. Backprop being first in line among those. But But we'll see a lot of things that it is unlikely to do, and we narrow down and try and constrain to families of algorithms that we think may be going on. So I'll show you a set of these constraints first, and then I'll go to some algorithm derivation from those, and then applications. So first of all, mammalian brains are all shockingly, unbelievably similar. If you take a neuroscience, a neuroanatomist, and have them look at the cortical structure of a mouse brain and a human brain, it is extremely difficult. You actually have to know what you're looking for to tell these things apart. They are shockingly similar. And there are, despite a long-standing search, we have yet to find any unique human structures that account for unique human abilities. And it's not for lack of trying, it's not for lack of funding, it's not for lack of smart people looking. We can't find anything in the human brain that is, the language organ, famously touted, and doesn't exist. And we don't know why, we don't understand. So, of course, we're left with this hypothesis that is possibly human-level intelligence depends entirely on getting the primitives right, because the entire human brain may be built up from primitives that are being done in simpler animals. And that there's a scaling argument. I'll talk about this repeatedly. So again, the aim is to pay attention to the bottom, pay attention to the top, and I'm just going to give you a little cartoons throughout, cartoons of what I mean. Low-level information like structure, objects, and motion, in the real, live, dirty, stinking world. High-level information like cognitive abstractions and inferences, and of course I mean, real low-level information. So, things like, of course we prefer, I say of course, but we strongly prefer videos to stills, partly because stills don't exist in your world, the biological world, and when we look at videos we get a lot of extra information. And for high-level information we mean, for instance, this is a little task that a group did, try to say something about like this little video. The penguin is walking along a grassy edge. He's looking around. He might jump down from there. There's the general AI task. Good luck with that. But that's what we want to try and keep our mind on is, this kind of question, being able to look at the raw data of this kind and being able to find these kinds of logic statements, if you will, or high-level statements from them. I'm going to summarize now in one slide what I'm going to try to talk us through. Brain circuits, of course, compute. What they compute is grammars, and I'll try and talk you up through that. And grammars, the things that get built by these brain circuits, encode time and structure relations quite naturally, and these hierarchically compose up to logic statements, which of course is ridiculously useful. And I'll go stepwise all the way up through low-level brain circuits, algorithms from these, how these compose, and we'll try to make an argument for that these things extend all the way from bottom through top. Little roadmap. I'm going to breeze briefly through these brain circuits and their constraints, the constraints that they introduce, that they impose on us. I'll show you how we derive algorithms from these. Then I'll show you when we put those algorithms together and run them on data, what kinds of structures do they build, what kinds of memories, representations, if you will, do they build. Then we'll use them on stuff just to see how they, for instance, in a couple of cases, how they compare head-to-head against some of the standard algorithms that are in the field. This is always a very useful exercise. We never want to ignore it. We can make theoretical claims for things, but at the end of the day, things are empirical. We have to understand them. Then I'm going to go from that empiricism back to mathematics and grammars and try to make an argument for more constraints, additional constraints on what kinds of grammars are being built and what their limits are. And finally, I'm going to make what is perhaps in this group an unusual pitch for paying attention to hardware. That is, I don't mean hardware per se, although I'm going to talk about it. What I mean is implementability. I mean, and again, it's part of the extensibility argument. If your software can only run on tens of thousands of machines in a cluster, we're reducing those down to smaller and smaller packages all the time, and that's good. But of course, what we really care about is how these things scale. That is, what kind of natural hardware would they embed themselves in, and how can we build large versions of them? Okay, we start with brain circuits. first I want to just briefly introduce, there are many places in the talk where we're going to introduce things that I'm just going to touch on and then not talk about just because I want to plant the seed that these things exist. There are 3 time scales. Evolution constructs brains, and we're going to talk about the structures that arise, but we're not going to talk about how evolution does this. Development is a distinct phase from learning. There are developmentally specific times. So for instance, you learn the speech sounds in your language during a developmental period, and if you don't, then you won't learn them the same way, and you learn the speech sounds in your language effortlessly, easily. And you learn the speech sounds in some other language as an adult very arduously, with great difficulty. People have their accents for their entire lives. This is interesting. So development is a particular set of algorithms, learning algorithms, and I have another talk on that and papers on it, but I'm not going to talk about it today. You can think of it as part of the way of sampling the world and, if you will, setting priors that then get used by learning, adult learning, which is what we're used to, which is building up representations from data. So I'm going to refer back to that. Brains began, mammalian brains, so there are brains and there are brains. There's reptilian brains, there's fish brains, blah, blah, blah. I'm a mammalian chauvinist. I don't care about other kinds of brains. When mammals invented this kind of brain 200 million years ago, they invented the neocortex, and the neocortex is the thing that is now 80% of your brain. It's not that you can do without the other parts. You can't, and I'm going to talk about that as well. The components of a brain are neurons and synapses, and interestingly enough, these are, when we pay attention to them, it gets nasty because these circuit components are things that no self-respecting engineer would ever use to build any kind of engineering device. They are probabilistic, they are slow, very slow, milliseconds. They're incredibly sparsely connected and typically randomly connected, and they're very low precision. They're crap. And yet somehow, no, for real. And yet somehow we are using these really terrible components to build high precision computation. And again, this is a design constraint. Something that the brain is trying to tell us when we are willing to listen. It's saying whatever algorithms you come up with, you're going to want to pay attention to how is it possible for them to be doing anything high precision when they themselves are low precision. And we will address this. So there's cortex, there's these other parts. Here's the striatal complex, the thalamus, here's the hippocampus, the amygdala. Each one of these things has very different cell types and very different wiring diagrams. And each of those distinct circuit designs gives rise to different families of algorithms in our hands and in the hands of many others. Much of the work I'm going to tell you about is stuff that we've done, but I'm also going to borrow liberally from great work from other groups. I'm going to borrow sometimes with attribution. So these are design constraints. The different designs of these circuits are giving different algorithms, so we're going to look at that. They're all unified in this big architectural organization, which we've got cortex talking in a loop with striatum and hippocampus and amygdala, and each of the stages of this thing, so cortex, posterior cortex talking to anterior cortex and looping, is that's a design constraint, and it's repeated over and over again. So we've got one of these big architectural circuits for vision. We've got one for hearing. You see this? Yeah. We've got one for touch. We've got them for much more abstract things that we don't even have easy names for. That architecture is repeated over and over again. It is argued to be the architecture of the mammalian brain, and it's probably the thing that will help us the most in understanding how it is that we do what we do. So we're going to pay attention to it, again, as a design constraint. This thing I said before, that brains are very similar across mammals, here's what I mean by that. This is just the primates, apes, monkeys. If we look at body size, and we look at the brain size, it turns out that just from body size you can predict very, very accurately what the brain size of the animal is going to be. And of course, not humans. Humans are the exception to this. We have these big, fat, bulbous heads that are not right for our bodies. And it's very interesting. The only animals that have these outsized heads are us and other animals of about our body size, like dolphins and porpoises and other primates. So interestingly enough, humans seem to be, for a moment, seem to be an exception to this rule of body weight going along with brain weight. One of the extra constraints that comes from this is that these brains are scaling across at least 4 orders of magnitude. That's a design constraint. Now let's look at, take the brain size, any brain, and now look at the components inside it, and let's see what happens. And it turns out that every single component inside your brain is tracking with its own little particular slope, is tracking in this lockstep fashion. That is, if you know the brain size of an animal, and notice how much less variance there is in this than there was just in the body-brain thing. These things are really tight. If you know the brain size of an animal, you know its neocortex size, you know its diencephalon size, you know its thalamus size, you know its hippocampus size, you know these things, which is weird. And the amount of variance, these little tiny places that are off the lines, that's all the extra part, the evolutionary specialization. And that's the question, is where the heck is there room in this? For adaptation, selection, evolutionary pressure, specializations. Where is there room for different animals, different abilities? And the answer is, according to these images, and a lot of others that are like it, there is not. And of course, humans, right smack dab on that curve. We have exactly the brains, and this is, again, this is not even a controversial notion in neuroscience. This is publication after publication after publication on this. Human brains are scaled up chimp brains. You take a chimp brain, scale it up according to these same allometrics, you find the human brain and all its components, including wiring diagrams, pathways, just the way it turns out. Which, again, is begging that question of, are we getting a qualitative difference, our abilities, from size changes alone? And so we want to beg that question, not ignore it, and say, is there a way that could be happening? Because it appears to be in our face as a design constraint. There's that architectural organization, one last little design constraint. And remember that some of these slopes are large, and that means that the proportion of your overall brain that is neocortex, if you've got a small brain, proportion of its neocortex can be 40% of your brain. If you've got a big brain, the proportion of the brain's neocortex can be very large, 80% in our case, because this slope is higher than these other slopes. See it? And that's exactly what happens. So we see these disproportionate changes in, again, completely predictable, but very disproportionate. Predictable according to those allometric curves, those slopes. So that's another design constraint. And now, that's all the design constraints I'm going to give you from biology. That was our little flyover. Now I'm going to try to go down into the circuitries and turn them into algorithms. So I'm going to give you a series of cartoons that are going to be derivations. Okay, here's the lembicortical loops, the thing I'm going to focus on, that we all focus on, it's 80% of your brain. This is, of course, a very simplified diagram, and it's still sort of a nightmare. Each of these are different cell types. They're wired up in these particular ways. What I'm going to do is I'm going to take this thing, simplify it a little bit further, and then this thing over here and this thing over here are the same, and all I've done is highlight them in light versus dark, highlight the parts of them. This sort of left little loop and this right loop. And I'm just going to walk us through a cartoon of what this thing seems to be doing in our modeling and what this part seems to be doing, and then I'm going to collapse them back together. So, and they actually have these names in neuroscience, so-called core loop and the matrix loop. Okay, core loop. We'll think about this by focusing on static objects. That is, when you're actually looking at an image, you're looking at me, or you're looking at a flower. The input comes in, the visual input enters here in this thalamic thing. It goes up to middle layer, it goes up to a superficial layer, and in many, many groups' hands, this superficial layer is doing the same thing. It's doing a simple kind of clustering. Basically, what happens is, as the synapses strengthen, the cortical response to slightly different inputs. Slightly different inputs give identical cortical responses after learning. That's the idea of clustering, and that's what these circuits do. They can be modeled as little competitive or winner take all kinds of networks in a very simplified form. So of course the effect of learning in this little network up here is to prevent the system from making fine-grained distinctions. And of course that's disappointing. That's not what we expect from learning. We expect learning to do something useful. And that is useful. It's generalizing. It's saying, well, now I don't have to see all the instances of these different objects, food or predators or whatever. I can just see a few of them, and I can generalize because now I no longer see them as different. I can get a single output to this input. That's the first feed-forward step. Now this thing feeds down to this deep layer cell, which feeds back to an inhibitory layer called the nucleus reticularis, which is inhibiting part of the input that was coming in. And of course the input's still there, you're still looking at it. So now you've just gone up, you've said, oh, I've got this thing, it's a category, it's a flower. And now I've subtracted something from it. What have I subtracted? That category thing, the part that's in common across a bunch of flowers, if this is happening over learning time. And what's left? Differences between different flowers. And that's what comes in the next cycle, the very next cycle. I should point out that these are discrete cycles. These are not, you're not seeing continuously. I know it feels like it, but of course you know in a movie you're seeing a series of still frames and they look like you're seeing something continuous. Your brain is chopping these things up into discrete parts and is using them as a series of, well, we'll see more about this, a series of snapshots. So you are seeing now the difference between these flowers. You're now categorizing the differences, which is a set of subcategories. You're subtracting those, and now what you're doing is clustering, subtracting, and cycling. And we can easily just throw away the biology for a moment, turn it into a simple algorithm, and start to think about it in terms of what is it doing to normal everyday data. It's doing a simple task of hierarchical clustering. So the first thing it says here is, oh, flower. Second thing it says is, oh, large petals or small petals. Third thing it says is, oh, color, whatever. It's successively subtracting off whatever makes a category and saying, okay, whatever's left, that's available to me now to make a subcategory. So it's categorizing, subcategorizing, subcategorizing. What we think of as recognition, I recognize that, it's a daisy. What we think of as recognition is really just a special case of categorization, successive categorization. There's no distinction in this, according to this model. Recognition is a special case of categorization. And also, notice what's happening is that it's reusing the same components iteratively to successively refine the category that it's recognizing over time, which is why it takes a little time to actually recognize these things. And we're much faster to recognize so-called basic levels than we are subordinate levels. So those time steps are iteratively using the same hardware to get finer and finer grained representations of the input. And that's one way in which we get high precision computations from low precision components, which again is this design constraint that's put on us. And this is one nice little trick that may be did I say trick? I meant principle for how this might happen. So we can use different kinds of data and use our intuitions on this. Here's a set of speech sounds. These are just a few letters in the alphabet, A, B, C, D, E. And the initial cycle of processing of these says they're all the same. They're all exactly the same thing. They're like form a little cluster up here. And they are. They're speech sounds. They sound completely different from car crashes and foghorns, and they are a particular kind of sound. If we now subtract the mean of this cluster, what we're doing is the equivalent of taking the origin and moving it up to the center of this thing. That's what subtraction of that mean means. And now we're in the middle of that cluster, and now we suddenly see, AJK kinds of sounds versus ECG kinds of sounds. We do it again, we do it up to this cluster. We see voiced CGs versus unvoiced AEVs. And again, we're saying, okay, speech sound, BD kind of speech sound, unvoiced versus voiced, and eventually getting down to the particulars of that category. Notice that it's only iteratively deepening. So for ones that are easy to tell apart, like B's versus Q's, it only iteratively deepens for difficult discriminations. It builds an unbalanced tree so that the shallow parts are the parts where the discriminations are easy, and the deep parts are where it has to continue to iteratively deepen to get more discriminations. We'll see an example of that in some detail. And again, assuming it's high-precision computation. We can easily just be responsible computer scientists and treat this as any other algorithm. We can look at it as, it turns out there's a big family of hierarchical clustering algorithms. It's actually two whole jugs. Anyway, it turns out that this hierarchical clustering algorithm, which just came from our modeling of this particular chunk of thalamocortical circuitry, it competes very well with the standard hierarchical clustering algorithms that are in the literature. Its space costs are linear with respect to the dimensionality of the inputs, and its time costs are actually sublinear as long as it's being put in appropriate parallel hardware, which of course in brains it is. And we'll want to think about as we implement these algorithms. Again, we'll come back to some hardware issues. So we can take advantage of the fact that they are intrinsically parallel. That was this portion of this thalamocortical loop. Let's now move on to this portion, matrix portion. So this thing we can think of as looking at things that are changing over time. Here's a speech sound. This is like bird, bird. And again, it's coming in there's a speed beyond which you can't hear. You can only hear these things in little divided episodes. Each input, so it's coming in like this, and you're actually hearing it that way, even though you don't realize it. There's a world of psychophysical experiments that show this. And now let's look at what the algorithm is doing. It's still coming in. The inputs are still coming in the same place they were, going up to here, becoming categories, but now they're being fed down to this other, not this thing that's subtracted, but this other thing that's now going to add in a funny way. And what it's going to do is it's actually going to do something like hashing, something like a Bloom filter actually. It's going to orthogonalize these things. It's going to take even very similar inputs, this unit here, even very similar inputs, give them different addresses, a la hash code, something like hash code. So what's going to happen? First thing is going to come in, and it gets fed up to here, feed forward, and then it gets fed back, gets its own unique name, and the second thing comes in, and that second thing is coming in here, going up to here, but it's arriving as this feedback from the first one is arriving. So it's chaining these things. Now what it's learning up here is the sequence of this followed by that. And that chaining is now, again, goes hierarchical. You get chains of these things, sequences. And so recognition in this case is now a special case of sequence completion. Again, we'll see this in action later. Again, we can turn this into an algorithm very straightforwardly, and we can do the space and time costs of this. One of the very interesting ones that I want to point out is that it scales linearly. The space costs scale linearly. And that means, so in other words, if we add more brain area, then we can linearly store more sequences. That is nice because it means, again, that the scaling is of the kind we want. We can make large versions of this, and we will actually get them. They don't show diminishing returns like so many algorithms do. Okay, now we've got these two algorithms, and of course they're in the same loop, and they're interacting with each other. Oh, now I want to briefly, the briefest ever, I think, possible presentation of the striatum, the hippocampus, and the amygdala all in one slide. You'll enjoy it. The basal ganglia in our hands and other people's hands is doing something like temporal difference reinforcement learning, and we're going to use that. The hippocampus is doing something that we can talk about in terms of compression and dilation. We're going to use that. Amygdala is doing something like filtering and toggling, and we're going to use that. So I'm going to without any introduction, I'm just going to simply use our work and other people's work as background. So now we've got these distinct circuit designs embedded in integrated architecture. This is just another cartoon for cortex and a bunch of subcortical areas. I see it several times. So we've got a little toolbox of algorithms derived from these circuits, and these tools include clustering, hierarchical clustering, sequences, chaining, hierarchical chaining, hashing, reinforcement learning, etc. Now we compose them into the integrated architecture, and we want to understand them. What does this instruction set do? What kind of computer is it? So now let's talk about that, how it operates and what kinds of things it builds. So here's that architectural organization. Again, I'm going to fly us through the first intuition. Again, there's several publications that make this derivation. If the individual cortical operations are categories and sequences, and the output from one region is the input to a downstream region, many in fact, there's fan in and fan out as you go successively through the cortex, then what we build are nested data structures, sequences of categories, of sequences, of categories. And those sequences of categories of sequences, that is a data structure. Those are, in fact, grammars. And we'll talk about the formalism of that. So what they build is, okay, so let's look at inputs that come in. Here's cats and faces and houses, and of course the early areas are simply these generalists. They're doing simple feature extraction, and they're feeding down to areas that are fanning out, fanning in, and finding possible joins of these things. So this plus this makes this plus this over here makes this, and they keep going downstream and separating into streams that become specialists. And so you've got region specialists, you've got rectilinear object specialists, you've got face specialists, you've got biological motion specialists. And again, those things are all stuff that is well confirmed in real brains. It really happens that way. You can find that level of localization. The representations within them are highly distributed, but the regions are specialized for the kinds of combinations of inputs that they are sucking into themselves to say, these are the kinds of things I want to look at. These are the kinds of things I'm a specialist in. So now we've got these nested sequences of categories, and they are grammars. And let's look at, so of course grammars are first known to us in their application to language. We look at them in terms of syntactic structures. What we're doing here is using them in terms of perception. I'll go back to it, but I want to just give you the language intuition for a moment. You've got a sentence goes to a noun phrase and a verb phrase, and you've got a noun phrase goes to, say, this one, an adjective noun, and you've got a verb phrase that can just be a verb, and you can make little sequences out of these. Again, they're sequences of these categories. The categories are themselves sequences of categories. That's all they are. His watch stopped, etc. When we use these for the raw inputs that we're getting from perception, we're taking pictures, we're making categories of these things, and we can turn them into these hierarchies, these sequences of categories. And from those, we can make, it's trivial, really is trivial, to take any structure like this and write a formal statement of what it's conveying. Anything with this label is a this, if X is a leopard. And so we can arbitrarily, so that's a simple step. So we can arbitrarily take memory hierarchies of this kind, build what we can think of as concept models from them. And this is where we have the hope of building these things up to higher level structures. Today I'm actually going to say very little about high level computation with these, but one of the things we're doing is collaborating with groups that do so-called cognitive architectures and trying to feed them raw data from this thing in the form of these grammar representations to see what they can do with it and what they can feed back. These things are already feed-forward, feedback networks. We'll see some of that as well. But we are hoping that we're going to complete the chain all the way up to more cognitive structures. These things enable us, once we've got them in this form, they enable us to make inferences. So if Bill hit Mary and John hit Mary, then, well, A hit C. And if Bill and John kissed Mary, then A, B, C, and each of these things can easily be factored into a simple statement, which looks strangely like a logic statement. And again, it's nothing more than the same tree that was being built up before. And again, you could see it easily, you could see intuition with language, but the same thing is happening with perception. So the algorithm overview is we look at features, we build up a relation construction of those, we build the grammars, we do this derivation of concept models, and we use those to make inferences, and we then cycle back around. Now, we now seem to have we started with a toolbox of algorithms that came from brain circuits. We built those up, they're building this complex kind of grammar, and see what they do. And they seem to lend themselves to structured data and time-varying data, which of course is nice because that's a kind of data that we often don't have good tools for. So let's see what we can do with it. Movies, sounds, and movement. I'll show you examples of these. Interestingly enough, although these tools can address things like movies and sounds, they also have, they degrade to special cases that can do things that we're very used to, like supervised learning, classification. So, again, being responsible, we can compare them head-to-head against the existing tools that do this. Let's do that. Here's our first example, classification. So, supervised learning. Here is an algorithm that is combining two things. It's doing sequences of categories, and it's iteratively deepening these things to build this hierarchical tree. And then it's doing a match-mismatch kind of operation that is a subcortical operation, that is a hybrid of hippocampal and basal ganglia operations. We talked about it in a paper, in a 2012 paper. And the basic operations are really simple. It's partitioning in a completely unsupervised fashion. So it's taking supervised data, partitioning them in a completely unsupervised fashion, ignoring the labels, and then it's looking at the labels and making a decision. What's that decision? It's binary. It says, should I cycle and do another unsupervised split, or should I not? Let me show you this on data. Here's a cartoon of high-dimensional, that pretend it's high-dimensional data, and there are these different kinds of objects. There's stars and squares and triangles and circles. What would an SVM do? Well, first of all, you have to pick one object, so let's pick green circles, and then you laboriously build a separator so that all the green circles are on one side, everything else on the other side. If you want to do that again for other objects, you've got to do it again separately. You can't do these, you can't do more than one of these at once. What does this thing do? What it does is it says, okay, I've got a big old space, I'm just going to do clustering. So I've got a region of the space here, these things look similar to me, and I don't care about their labels. And then I look inside each of these unsupervised clusters, and I say, oh, well, is this guy pure with respect to those labels that I ignored? So let's look at it. Well, this one is, this one is, this one is not. So now I'm going to just mark these guys as pure, and I'm not going to iteratively deepen them anymore. And I'm going to take these other guys, and I'm going to go further. I'm going to say, look, unsupervised split. Again, completely ignoring the labels, unsupervised split. So I've got a region here, and I'm going to check those for purity. And I'm going to leave them alone when they're pure, and I'm going to keep iteratively, unsupervisedly splitting when they're not pure, until I get to something that's pure enough, and I can set a threshold for how pure they're going to be. When we're done, what have we got? We've got a hierarchical tiling of this space, and we now know a great deal about the objects in it. Not only do we know that there are stars in certain regions, and there are circles in other regions, but we also know that there are different kinds of stars. There's stars over here, there's stars over there, in different portions of the space. And of course, the SVM cannot tell you that. We also know the hierarchical organization of these things, that these are special cases of these, which of course the separator can't tell you. So, two questions. One, how does this mechanism compare in terms of efficacy against this, and how does it compare in terms of cost against this? This is all published work. Here's percent correct. This is the SVM on a series of, this is a particular Caltech data set, and very simple one. And what we see over and over again, we've got many examples of this, and we can explain why. Intuitively, what it's doing is it's making finer grained, it's doing a lot of what the SVM tries to do. It's making finer grained subcategorizations precisely where there are difficult discriminations because two different categories are near each other, right? And so it does it slightly better. And when you look at the ROC curve, you can really see that it's getting slightly better accuracy with less false positive rate. Again, that's partly because it's shrink wrapping a region around the data that are within that volume of the space. So it's making less generalization gradient around that, if you see the intuition of that, which is nice. And the time cost is the most useful thing, which is here's the time it takes for an SVM to learn these hyperplanes, here's the time that it takes the CSL system to learn this full tree. The reason it's so cheap is because it's only doing incredibly simple operations. It's doing unsupervised clustering, and then it's making a binary decision to either split and do it again or not split. And that's it, that's the entire cost. So it's very cost effective to do it. All right, let's talk about the kinds of,
Yeah, I was just wondering, was there a generalization error there?
Was there a
generalization error? So is there any off-training set data?
Well, so that's why I showed you an ROC curve. So these are the false, so along the x-axis is the false positives. This would be a set of things where you're mistaking something for one category. And on the y-axis it's saying, here's where, if it is in category X, then I call it an X. Here's where it's saying, how often do I call a Y when it's actually an X? And so where you want to be is way up here in this left-hand corner. That's telling you that you're making very accurate categorizations and very little false generalization. And what you see is that both the SVMs and the cortical algorithm are in that region, and the cortical algorithm a little bit more so. Does that help? Is that addressing?
Yeah, so the algorithm saw all the data, all the training data. The learning.
They both see the exact same training data.
Right.
That's right. That's right. So everything they're being given the same inputs.
But you don't hold any back. You have no holdout set.
Oh, sure. When you the way to test it is to let me go back. So here, we're training on 10% of the data and testing on 90%. Here we're training on 70% of the data, testing on 30%. So we can just show you throughout that curve how much we're holding back, and then we're doing a round robin to test for the generalization. Is that?
Yeah, it's just that with the SVM you'd expect it to generalize better because it's forming a partition that just separates the two cases.
No,
So
the reason you don't is because here's what it's doing. It's saying all the yellow stars are on this side, all the others are on this side. So if you get a point, in a region like this or a region like this, it's difficult to know that it's trying to shrink wrap to that separator, and SVMs are focusing on exactly that region of the space. What this thing is doing is it's making a shrink wrap around just the data that fall into a subcategory. So in this case, it's got a shrink wrap around a polytope around these yellow stars. It's got another one around these yellow stars. And so it's actually making less of a generalization gradient away from the data than the SVM is, interestingly enough. And that's a sort of an intuition as to why it does slightly better. Okay, let's look at auditory data. Oh, wait. I don't know if you may hear it, but let's see if you can hear it. She said blue twice. These are the two spectrograms. And of course, the speech recognition task is taking these data in and trying to match them against each other. Let's see what the sequence of category algorithms do. They see an endpoint here, a feature. There's a little feature. They see another feature, an endpoint there, another feature, and they've got a sequence between them. And now here's another one down here. And now here's a sequence of those categories of sequences. And here's a sequence of categories of sequences of categories. And here's a sequence of sequence. And as you build these things up, as you train on these sounds, what you're learning is a skeleton recognizer of the reliable repeated portions of the input and the relations between them. So features and relations, categories and sequences. And now the task is to match these two against each other, not to match these things against each other. So the question, of course, in our testing is this a useful representation for doing that kind of testing? It looks like it is, using those learned grammatical relations. One of the recent tasks that we've done is taken a large amount of speech data. This is Moby Dick, and we take actually multiple text, audiobooks. We just take audiobooks that we buy and multiple speakers, and we try to see what kinds of speech sounds these things are learning, and we're generating these. So we've got a motor component. I'm going to come back to the motor component in a minute. Motor component that's trying to generate what it's learned, and it then composites these into longer sequences. So it's it's extracting repeated speech sounds, things that recur in an unsupervised way, compositing these into sequences that can occur in more complicated objects, and they're all in the form of little grammars, phoneme grammars, if you will, speech sound grammars. And now we try and get it to produce sounds. Oh, skipped it somewhere. But anyway, it's trying to learn how to. I'll let it go. It's going to come back. Here are the kinds of sounds that it picks up. I don't know if you can hear them. Oh, and notice that the different corpus will give you different speech sounds, naturally enough. And these composite to longer ones. And we're using those to try to do two kinds of things. One is to see how they're used to understand new sounds, new sound sequences that it hadn't heard before. And the other is the extent to which it learns to produce sounds within a language. These are, I'm going to do a quick side trip back to the brain when we started, just to say, when you look at, for instance, categorical perception in speech. So when you hear the sounds ba and da, if I make a computer-generated set of them, I don't have them on these slides, but so there's ba over here, da over here, and there's a continuum in between. So this middle one sounds equally like ba and da. What do people do? If you ask them, is that a da? Here they say no, here they say yes, and here they get it wrong. So even though this guy here is like almost equally ba and da, doesn't matter to them. They're like, oh, that's a ba. That's all I hear. And so now we can look in the brain and see the same kind of thing of iterative deepening, that is successive downstream brain areas that are selectively active only where the discrimination is difficult. Here's the easy part of that curve. It's the edges, the ba part and the da part. Here's the, can we see it? Yeah. Here's the hard part of the curve in the middle, where you have much more trouble telling what they are. And here's what we see is, if you just look at the easy ones, you've got a region right here which is extremely near your primary auditory cortex. Your primary auditory cortex is right there, and these things are right next to it. So they're saying, I got no problem. This is easy discrimination, and it's either a ba or a da, and I don't need to go any further downstream in my brain to look for that. And as soon as I get to the difficult parts, all of a sudden, there's no auditory cortex involved. It's all way downstream to these far-flung areas. This is work by Uni Lee, published in the last few years, showing that you have to go, you're building these things to go downstream, you're making deeper hierarchies depending on the difficulty of the discrimination. I'm going to skip localization, I just skipped it. Let's go to vision. I mentioned that we like movies. Movies are great because we've got all these extra cues that are not present in stills. Motion cues, contiguity, structural poses, I'll show you examples. So of course we use optic flow throughout to the optic flow field to show us where motion has occurred. So for instance, in this picture from Call of Duty, there is a human, and you can't see him. But you will in a moment. Wait for it. Oh, here it comes. Wait for it. Oh yeah, there he is. You won't see it again. So there it is. As soon as he moves, you can't miss him. It's like human shaped, it's making a biological kind of motion, you can't miss him. And there's nothing in any of the stills, nothing in any of the frames that gives you that information. Right? There's nothing there that's human shaped, there's nothing that's telling you in any still that this is a human. It's only the motion that's doing it in this case. That's an extreme example. Here's two objects. If we had these two pictures, how would we tell that they're the same object? Well, of course, it's extremely difficult, unless we have a movie, which is giving us contiguity, which is a form of, if you will, of free supervision. It's telling you that, oh, this thing becomes that thing, frame by frame. Structural poses are useful, where we've got the difficulty between, which legs are which, and how are they moving separately from the animal. And of course, when you have a movie, it's showing you what that articulation is. We'll talk a little bit more about articulation in a moment. And that gives you the various kinds of deformations that objects can go through, which would be possibly quite difficult to recognize if they were stills. So what we're doing, I'm going to just skip. What we're doing is, so here, we take a movie, we superimpose the, here we go, the optic flow over it, and this is just optic flow again, but now it's easier to see because the angle of the optic flow is the color, and the depth of the color is the velocity. So, let's do it again. And now you can use it. You can use it to, and we're actually using these things called superpixels from a guy named Felsenschlag, who did a great job. We're actually modifying these in another paper, so that we can segment the movie using motion. And of course, we can use that to make standard bounding boxes. I'll come back to this. Bounding boxes are lying to you. They're making things appear much simpler than they are. So we can do the same thing repeatedly with different kinds of movies. And of course, it's going to learn now. So we've got lots and lots of movies that we just download from YouTube, and it's going to learn all sorts of objects that are in it, in the movie. So in this case, it's going to learn that thing over there. I don't know if you see it, which is a, I don't know what it is, a puddle or something. But it occurs a lot in these videos, and so it learns it. It's going to learn that thing, which is a shrub. It's going to learn, and it's also going to start to learn all these different images of the different articulations of objects, the different parts, which I'll come back to. Let's now talk a little bit briefly again about those bounding boxes. Here's an image of Dartmouth. Here's a bounding box that's easily derived from motion in the image. But if you actually look at the superpixels, the components of each frame that are being recognized as being part of that object, what you see is they're awful. And the bounding box is just hiding this. The bounding box is making it look like we've got it down. But when you actually are looking for the actual pixels that are parts of the object, you don't have it. And here's an example, particularly egregious one, of just how bad it is on frame. If you're only looking frame by frame, it's incredibly bad. So one of the things we're doing is looking for articulation, and the way we're doing this is by taking objects, both in the real world in this case and in simulated worlds, and looking at them moving, and using the contiguity information to tell us that this still is now transforms to this still by this motion. And that little map of a still and a relation, two stills and a relation between them, is what enables us to then start getting better and better. So this is an intermediate example of finding superpixels within a highly articulated object that's difficult to see. And of course, we're literally using the Mechanical Turk to get people to label these things for us. Okay, so far I've talked almost exclusively about perception. I want to briefly talk about motor actions. The same memory structures are used for motor behavior. Here is just perception. We're now going to move the dog's arm, and what we see, you can see over here, I don't know if you can, yes you can, sure, that it is perceiving the arm motion that we're putting it through. And then when it is walking, it can perceive the arm motions that it itself is putting itself through, and it can compare those, and it can start to learn mappings between the perceived somatosensory, the touch representations, and motor representations. Very useful, because then what it can do is it can say, oh, now I can try to corral motions that I know of to try to get me from one position to another position, which it fails to do. In this case, it's using reinforcement learning to do this. It trains quite a lot to do this, and it eventually gets a way to get from any position to standing up. Now that was in simulation. We do it in simulation for a reason, because it takes forever. When we do it in the robot, first, so we've got this, here's a robot that's going to track an object, simple task, actually watch where it goes. Here's an object, here's a robot that's going to do, it's doing simple hand-eye coordination. It's not actually doing, I don't want to pretend, it's not actually doing the cognitive task of solving a terror vanilla here, it's just being coordinated. Here's a robot that's learning a bunch of positions. So what it's doing is it's saying, whatever position I'm in, I want to see what kinds of moves I can make that'll get me in some other position. And I want to catalog those, make a big memory structure of those, so that I can use them when I'm in some unknown, unpredicted position, and I want to get to a different position, like standing up. This is beginnings of the theory of yoga. So it's building up memory structures that are related to perceptual structures, can be learned in tandem with them, so that it can carry out these motions. So we're doing a lot. We're doing stuff with robots, but we don't want to be training robots in the real world if we can help it, because it takes forever. And so what we're doing is we're taking. It turns out that the world has decided to work for us for free. These guys building things called video games, I don't really understand it, but they're building photorealistic environments. And so we love them, because what they're doing is they're giving us free testing grounds where we can control it. So we've got this little controller that's doing perceptual front end, building representations, making decisions, and sending out outputs, which are candidate moves into the game. And then we've got a gaming rig that is putting out a state. Here's what, and the only state information that we're using is what's on the screen, visual image on the screen. None of the background super secret vector information. We're just using whatever the gamer sees. And we're taking in moves that the simulator wants to build. And so put together, it's now being able to laboriously train itself in video games. And it can do very little in this. I'm going to show this is now a human user running through the game for us. And what we do is we take episodes where somebody gets shot, and we then learn those as here's a sequence leading up to, it's a little blame assignment, sequence leading up to somebody getting shot. And we start to put those together and build them into sequences that we can then use to track objects, and we try to learn what kinds of objects we can track and what kinds of objects interesting enough not to track, which is also important in these games. And what we really care about is not playing the video game. Again, it's not doing the gaming part of it at all. It's doing the visual recognition of states part of it. And what we really want to be able to do is say, let's try and train it in something that's reasonably photorealistic, and then transfer it, and see if we can download that to the robot, and see how much training time we can get away with not using in the robot to, how much of a leg up do we give the robot now when it's pre-trained in the artificial environment. So partly we're doing this to training in one game, trying to go to another game. Very limited success so far. And again, these games are getting better and better, more and more photorealistic, and that's nice for us because it's suggestive. It lends us hope that we might be able to do more training in the game and actually have it count for something when it gets downloaded to the robot. The idea is to download the robot. We have a simple version of this from a couple of years ago. This is the robot actually wandering through the field. It's only looking for in this case, very simple visual cues. These little bullseyes, you can see one that we've just pasted up. But it's got to arbitrarily search, think about where it's been, and try to find new bullseyes that are put up. Okay, now, quick side trip to grammars. As I pointed out, these things grow, and we can make inferences from them. We can, by simply adding one little thing to a grammar, like the fact that there's such a thing as adverbs, we get an enormous disproportionate increase in the number of sentences that can be recognized. And indeed, you get, so this tiny little quantitative change to the grammar has a very, very large qualitative change in the kinds of sentences that it will accept. So we hypothesize that we'll be able to build up from these brain areas with increasing brain size to the simple algorithms that we have started with, the elements, the tool set, the instruction set, and building up from these to what we've seen, positional categories and imitation, the beginnings of symbolic descriptors, and the kinds of things that we want to get to, rule-based reasoning, and referential language, and possibly beyond. Interestingly enough, you can tell what kind of grammar you have by what kind of machine you have. If you have a finite state machine, you've got a regular grammar. If you've got if you add a memory to that thing, a single stack pushdown in this case, then if you add a restricted stack, you get visibly put down, pushdown grammars. Unrestricted stack, you get well-known context-free grammars. If you add a nested stack, you get something called triadjoint grammars. If you keep adding multiple nested stacks up until arbitrary numbers of them, then you eventually get up to the family of so-called indexed grammars. And those are extremely powerful. They're often hypothesized to be the size that we may be using in human brains. And you might ask, where are the other famous ones that we've heard of, like context-sensitive grammars? And they don't exist in this world. In order to make a context-sensitive grammar, you have to have a parallel stack push-down memory. You can't do it with a single stack. And so if you have bounded stacks, you immediately get context-sensitive grammars. If you have unbounded but halting, you get recursive, you get so-called turn-complete stacks, then you get recursively enumerable grammars. And none of those occur if you've only got single stack pushdowns. And we and some others have hypothesized that this may be all you get in brains, and this may be therefore the limit of the size of the complexity of grammars that you can possibly build from brain circuitry. And that may, if that turns out to be true, that may be itself a design constraint. It's what we're actually doing experiments on now, we and a couple other groups. Okay, briefly, we'll go to hardware. Adding cores does not give you speed up. That's why your quad-core machine is not 4 times faster than your single-core machine. The reason it's not is because the software doesn't know what to do with it. You can think of that as Moore's gap. People have disparagingly called it. And Moore's law is the rule that's telling us where the power will come from. You've got this variable s. If you've got very intrinsically parallel algorithms, then you can throw cores at it and you will get speed up. If you've got a very serial algorithm, you throw cores at it, you do not get a speed up. So inherently serial tasks do not speed up with the addition of cores. Inherently parallel tasks do speed up, and they can speed up as much as the number of cores that you throw at them if they're really parallel, and if you use the cores right. With that, so anyhow, I'm sure that sympathetic ears in the audience, people who have built things like vision systems and have and the code is intrinsically parallel, as it is in our hands, and your hardware is artificially slowing it down. And it's a nightmare. You can't, when we built the first of these several years ago, we literally couldn't even, we could barely even run it. You had to, so we of course went to GPUs, and we had to recode everything. Anybody who's ever coded for a GPU, condolences. It's not something you want to do on the worst day of your life. And you have to, you have no choice, because you need the parallelism. So we were looking for, we have a hardware budget, let's go out and buy parallel hardware that takes our code, recompiles it. It's already, we don't need anything that parallelizes anything. We've got intrinsically parallel software. And all we want is hardware to run it on. When you find it, send me you can tweet me, because I haven't found it, and it's not out there. So there's a group that's building from these brain-like systems simple learning rules, low precision connects, sparse connectivity, modular, and they're building parallel hardware that is intended to take these algorithms, brain-like algorithms, and run and give them their due, run them as fast as they are supposed to be, as the software says they can be run. And these are a bunch of publications and several patents actually as well, and they've got what they taught me to say is metal on a desk. That is actually is real, runs. It's a real hardware system, and this is enabling. There's all this talk about the Internet of Things, and what they forget to mention is that you're not going to have no Internet of Things until you have computational hardware that's going to enable things to be run in massively parallel fashion in very low power, tiny boxes. And right now, we do not have those things. And this is hardware of this kind, running brain-like software of this kind, may be one of many enabling platforms that gives us a chance to build things of a kind that we simply can't build right now. You can't, again, literally, when we were building that vision system, we literally had to run, every cycle would have to run for several minutes at a time. And to run any actual example, we'd have to run it for weeks and then wait. And then we couldn't even debug that way. We can't live like this. So the hardware is not just an amenity. It's not just an afterthought. It can be crucial. It can be enabling. Here is an example of current Intel system. They're really trying to track the bus. Notice that the parallel hardware has already found it. This thing is still looking for it. There it goes, found it. Yeah, that's not working out. So the trade-offs are, forget the power thing, but at a particular power setting, it will give you a 200x speed up. And again, it's on a desk, it does this. And just to put that into human terms, that takes a 4-hour task, and it makes it 71 seconds. That's what a 200x is. That's real. That's changing your life. That enables certain kinds of things to be done. We don't have autonomous drones now. We have handmade drones, and we don't have autonomous anything. But of course, you're not going to have autonomous mobile systems until you have hardware that can be put on those things that is small enough, light enough, and low power enough to be runnable. And so we've got this drone back in the lab that if we put this processor on it, it gets a 87% reduction in power use, 70% reduction in payload weight. And what that translates to is how far it can fly before it's going to die. What kind of mission can it be sent out on? So we can, I skipped it. We can run it, this is it running in a lab, and it's going to, this is the kind of task we wish it to do. It's wandering around looking for a particular kind of object. In this case, it's going to be a laptop. I know it's coming. Laptop, there we go. It's doing that there too. Here, it's going outside, it's looking for cars. If we do it with just superpixels, we can see again how difficult that is if you're just going frame by frame, which we're not doing, but I just want to illustrate how difficult the problem is. And what we're doing again is learning articulation, learning what does a car look like in all its different rotations, so that we can teach it to generalize across frames using OpticFlow, with the intention being that it will be able to do what it cannot do now, something like this, of actually recognizing the different pieces of the car. All right, I've taken brain circuits. We're done. We're done. I've taken brain circuits. I've shown how we can derive algorithms from them, shown you what kinds of representations these build, shown you how they give rise to applications, and also how they compete head-to-head against other things that we already have for those applications, including classification. I've talked a little bit about grammars and what the limits of these things are, and I've talked about how these, because they're intrinsically parallel, they lend themselves to parallel hardware, and with the appropriate hardware, we may be able to do things that we couldn't have done before. So I've got, the argument is that we're building towards unified vision, audition, learning, and navigation with representations that can be input to a full cognitive system. They're not hybrids. We're using real data, not clean data like the dreaded Caltech 101. Low-level algorithms compose, as we've seen, up to arbitrary logic statements, and they should be able to integrate, they should be able to feed themselves to systems like SOAR, which we're now experimenting with. They're intrinsically parallel, so they actually can extend, they can be used in real world, both real-time and real small packages and energy-efficient packages. And they're also concordant with the things that are easy for humans are easy for these algorithms, and that intuitively suggests, we hope, extensibility of the approach. you very much. Yo, questions? Yeah.
Can you say a bit more about the hashing bit and how it will be implemented in Cortex?
Yes, yes. Oh boy, let me see if I can find. I will try. Take this back. So this bit right here, there we go. Look at that. So this bit right here that is, there we go, doing hashing. It's really doing something. We've actually got a paper on this. For anybody who wants it, Rodriguez et al. I want to say 2004. And what it's really doing is something that turns out to be a Bloom filter, which is typically used for spelling correction. It's making a unique name for for every different input. So it can be used as a subpart of the hash code. It's actually not doing full hashing. In particular, what it's not doing is recovering from collisions. So if things collide, if it builds addresses and they collide, it will start making errors.
How is that implemented in Neurons?
So the paper actually, the 2004 paper is actually appeared in the Journal of Cognitive Neuroscience, and it's actually a very neuron-based thing. Okay, so these neurons in the non-specific thalamic nucleus are, so there are several examples, there's a bunch of labs that have shown that they're temporally dependent. That is, they will, if you put in AB, it's different from BA, and if you put in several of these, you've got very fan-out architecture, so you've got architecture that doesn't lend itself to categorizing. Things don't converge. Every new input gets mapped, it's physically mapped to a different set of different distributed representation. So it's really the anatomy that's doing the trick in this structure. It's doing, and again, there's plenty of examples of neural networks that do this kind of thing, orthogonalization, if you will. So I don't have a picture like this, but every input is being mapped to many fan-out target neurons, and they are temporally dependent. So so the likelihood that you will get, and this is what we calculate, what we actually do is, well, I don't have a slide for it, but what this little equation is doing is saying, what's the likelihood that you will get the same distributed representation out from two arbitrarily similar input vectors. So you take two set of input vectors, and you can test how similar are the outputs from those nearly identical inputs. And what you get from that is a capacity estimate. So you get, you see what I'm saying?
Yes, but the readout is not going to be an arbitrary thing for every particular pattern.
The readout is going to be a uniquely assigned name, a newly assigned name for every pattern, yes. Or maybe I'm not understanding.
So you mean there's going to be a neuron that only fires for one?
No, a pattern, not a neuron. These patterns contribute to, or participate in many different patterns. Yeah, I'll give you examples. Very much, a very similar calculation actually was recently done by the group that was looking at movie star neurons in epileptic patients. What they had were electrodes that were in place in medial temporal lobe of epileptic patients. They're there, the epileptic patients have to just sit in the hospital, they're bored, they have to wait for a seizure to occur, and only then do the electrodes give us any useful information for epilepsy. But in the meantime, they're giving us lots of useful information for other tasks that we can give these patients. You show them a bunch of pictures, and you start to see that there are patterns. There's no grandmother cell. There's no cell that is firing just to Jennifer Aniston, but rather there is a pattern of cells, and that pattern is firing over and over again to different versions of the same actor, or different versions of the same president, or different whatever different pictures you've got. From that, you can actually make an estimate, a gross estimate of how distributed these representations are. That is, how often is a cell participating in more than one representation and still being able to be told apart. So in that case, these things are doing categorization in that region of the brain. In this case, what they're doing is they're still, each neuron is still participating. There's very straightforward math that goes with this, and it is published. And you can calculate how likely it is that you will get non-overlapping addresses, vectors that are corresponding to each of the different inputs that you're giving. Hope that's helping. I know, I will show you the video. Yes, Peter.
Yeah, the part where you talked about the second memory step and the limit of on the grammar.
Yeah.
Why I didn't get why the brain couldn't have a second.
Oh, we have no idea. No. Sorry, then I misspoke. I apologize. Nobody has any clue whether the brain has that or not. We have no idea. There's a reason why we make that. We and some others make that argument. The structures that we know of, they're not really doing that. They don't map that directly onto that mathematics. But if you look at the difference in kind that you get when you simulate networks of different sizes, if you just assume that you're expanding those stacks, then the simulations suggest to you that you're hitting a limit with that. So that's simulation work at the moment. We don't know neurally whether it's possible that we can go beyond those grammar structures. And interestingly enough, people who have done this work on language and on other kinds of capacities have suggested in the past that the indexed grammars might be the appropriate level for enabling us to do the kinds of natural language that we do. They haven't gone to the level of context-sensitive grammars, but there hasn't been a brain-based argument as to why that might be until this work. Yeah.
Just maybe a follow-up question. So in the natural language examples you gave, the John kissed Mary and stuff, there wasn't explicit recursion, but I assume there's something like that in the way that you're doing.
Actually, no, great question. So there was a popular thread for a while suggesting that what language enables us to do is recurse, and that's what you're referring to. Yeah.
Yeah, this kind of flourish of activity about 6-7 years ago.
Right.
The big
right.
debate about recursion, and it seems to have gone away.
Well, partly it went away because the person who published it went away,
Yeah.
which is an unfortunate story. But you can look it up. But anyway, we actually have very limited. The empirical evidence suggests that we have extremely limited recursion. And the moment you get beyond 2 or 3 of these, you try to say, you know, the man, the boy, the girl, hit, ran, read. I can't do it, but linguists are famous for this. That's why we keep them in linguistics departments. And we, sorry. But you can come up with sentences that are recursive and are parsable, but they're not the kinds of things that empirically people can do. And this is often, the linguists often argue that this is a so-called performance deficit as opposed to a capacity deficit. And there's countervailing views. It does not do full recursion. It does nested sequences. And how deeply those can nest is only as deep as the examples that it's given, because it won't deepen the tree any deeper than those. So it was a question of how much you can actually process.
But in other words, it's not some hard limit like some people have proposed. There's no point in talking about structure.
No.
Okay.
It's not a hard limit. No, absolutely not. Yes, Paul.
So, what is known about the timescales of the core and the matrix loops?
Good. Typically, alpha. So about 100 millisecond cycles. They're working in tandem. And you can see these things happen. This is where, so all EEG waves are is, you're measuring practically on the surface of the scalp, what you're seeing is coherent activity in lots and lots of neurons. Otherwise, you wouldn't see, there would be no coherent EEG. It's coherent because it's lots of neurons. So you're seeing a certain kind of synchrony. So when you see a theta wave, you're seeing synchrony at 5 hertz. When you're seeing an alpha wave, you're seeing synchrony at 10 hertz. That range of theta to alpha is widely implicated in this kind of recognition behavior. So whether you're doing vision or audition, you're in that range, and you can show that there are limits on this. For instance, if I play you 3 sounds, bum 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 versus bum bum bum, and I play them fast enough so they go below the alpha speed, you can no longer tell which order they occurred in. Although psychophysical literature on this.
Does that mean that actually each level of the hierarchy in the clustering is taking 100 milliseconds? So
Oh, good question. There's actually an interference. When things are moving, I have a slide for this. I don't know if it's a pretty fun slide. It's a group, and George Alvarez from Harvard did this work. Basically, here's what it says. There's an interference effect. So that iterative deepening can only happen while you're looking at something. If the thing is moving or changing, then the matrix system comes in, and it's now generating its sequence chaining things, which get in the way of that successive deepening. So when things are moving, you will not see them below the basic or one level below that level. And indeed, it turns out this is borne out in behavioral experiments, psychophysical experiments, where if you see an object and it's the objects in it are changing, and I'll find a slide for you in a few minutes when we're done. And then you rotate the object like this, and all of a sudden everything looks like it's standing still. All the parts of it are standing still. You can no longer see them changing. It's really like, you can't believe that it's happening when you see it. This was subsequent work from ours, we weren't involved. But again, it's just one of several experiments that are suggesting that you're able to iterate down as long as you're focusing. And as soon as you're not focusing or something's changing, then you're stuck with a particular category level. And you'd have to relearn to specialize at that category level if you're going to look at it over time. And we've got work that uses that interaction, but it was, I would say, beyond the scope.
So we better hold it to one more question so that lunch doesn't get compressed too short. So who has the most interesting question?
Someone, go ahead, you always do.
All right.
I don't understand the wisdom of looking at the brain for artificial general intelligence.
I know you don't.
And it applies to the previous talk.
Say again?
It applies to the previous talk as well.
Right.
Wouldn't it make more sense to aim at a mathematical level of description?
No, and the reason why is, it's a great question, and I couldn't be more happy that you asked again.
Finish asking.
Oh, please, go on. Okay.
I wanted to connect the complaint that I have to the problem that you posed us earlier in the talk. Similarity of brains viewed anatomically, I assume. What the heck is going on? Well, we know what's going on in general because of the people who focus not on anything local, but on the math. That is, a massive Turing machine can just print all names, or it could do something sophisticated based on what the program is. So focusing on the hardware is not relevant. I don't get it.
Great. The hardware there is no software in the brain. It's all hardware, it's wetware. And the algorithms are being carried out by neural activity, by the activity of the hardware itself. It brings us to the real answer to the question, which is existence proof. AI has been trying, and neural networks, and name your favorite fruit, has been trying for some time to generate artificial intelligence, and logic systems have been trying for some time to generate general artificial intelligence systems. And it's like Clint Eastwood would say, how's that working out for you? It's that we have been stuck. We've been stuck for a long time. And it's not, I'm not pretending that I'm working out that much better. I'm trying a different track. And the reason I'm trying that different track is because of the existence proof. We only know one set of algorithms that does this. we can make the argument that says, oh, there's a space of possible intelligences, and humans are just one point in that space. And I suggest to you that that is a very curvy space, and that the neighboring land is not going to be the way you think it is. And of course, there are no existence proofs yet. None, zero, zilch, nada. No existence proofs of any of these others. And so I think it behooves us, the intelligent, pragmatic, boots on the ground way to behave, is to look at the thing that actually does the task, is to look at the existence proof, is to look at the wetware, is to look at the things that brains, humans, actually are doing, as opposed to conjuring, imagining. Not yet. We'll get there. We will get there, we hope. But right now, we are stuck, and we've been stuck for a long time, and things are starting to move in a good direction. And in part, they're moving in a good direction because we've been looking at brains a little bit. And I think the more we look at brains, the more it's going to help. And we will, I know, continue this discussion. Thank you.
All right, well, thanks.